So it has been given in YouTube also. It is now seen in YouTube also now.
So the live is on, sir?
Sorry?
Yeah, is the YouTube live on?
Yes, now YouTube is on. Then also,
but it's not showing us this.
Maybe a little bit time it will take.
Okay.
Just I said now on live.
Okay. Now it's okay.
Okay. It's coming now? Yes, I understand. It's now coming.
So, Dean sir.
Yes, please.
After the speaker's introduction, you will ask him to start, or should I ask him to start?
You can.
Okay. How many people are watching on YouTube till now?
বুঝতে পেরেছি ওটা আমি এখানে আমার স্ক্রিনে ফুল করে দিলেই হয়ে যাবে ওটা আমি এক্ষুনি করে দিচ্ছি হ্যাঁ
Dean sir, maybe you can introduce Tapunda to other, all of our faculty members. There are quite a few are present now.
Yes, just I am doing this thing. Professor Nayak, it's our very pleasure and honor that you are with us now at this moment, and we will experience a very informative also talk. Before that, I wish to just request our head of the department, Dr. Moumita De. He is the head of the Department of Physics, Adamas University, to introduce of all our faculty members in the department to you. Please, Dr. De, you can introduce our faculty members to him.
Okay, sir. Thank you very much. Hello, sir. We already met. We have met in the last session.
Yes,
so, yes. How are you, sir?
Good.
Okay. So I'm seeing that some of our faculty members are already present today. So if you can please, and let's see who is present. Professor Aparajita Bhattacharya. So let me unmute you. Ma'am, can you please unmute yourself? The sound is not very good, ma'am.
Ma'am, you can hear us?
Is it okay now?
Yeah, somehow.
Better.
So actually, Professor Bhattacharya is a professor of our university, and she will be one of the moderator of today's session. Ma'am is was the HOD and a professor of Department of Physics, Jadavpur University also. She is working on nuclear physics, nuclear astrophysics, etc. And some of other faculty members are also present, I think. So let me introduce to Dr. Shatrupa Bishwa. Shatrupa, are you here?
Yes, ma'am.
Dr. Shatrupa Bishwa. Hello. So if possible, please switch on your video. We can't see you.
Actually, a problem with the bandwidth.
Okay, no problem then. Shatrupa is an assistant professor of our department. She is on biomedical engineering. And let me see. Some other faculty members are already joined. We have amongst us Dr. Moumita Mukherjee. Moumita ma'am, are you there?
Yes, I am here. Let us start.
Moumita madam is our associate professor of our department, sir. Ma'am, if possible, can you please switch on the video?
Yes, ma'am, we can see you. Camera is a little bit down.
Shobuj is there, I think.
Hi, everyone. Good afternoon.
Shobuj is there.
Hi.
So I think with time all the faculty members now, a lot of other people are also present, so I cannot distinguish very much.
Okay.
Okay.
Anjan is there. Anjan.
Anjan. Anjan, are you there? If possible, please switch on the video. Yeah. No, I'm just introducing sir to our faculty members.
I'm not able to start my video. Why I don't know.
Okay, no problem. Your voice is sufficient.
Okay. Some network issue maybe.
Yeah. So let us wait for a few minutes. I think.
Hello, sir.
Yeah, hello.
Sir, this is Kinkor.
Oh, hi, Kinkar. Yeah.
How are you, sir?
Good. I thought you looked familiar, but now you have a you look slightly different. So.
Yeah, he has joined colleges now.
Oh, okay. Wow.
He got his job.
Yeah.
Yes, sir. I have joined in the last CSC.
Oh, okay. Oh, very good. And Sudhika?
Yes. So Shudipa is also here.
Okay.
Yeah.
Shudipa has also joined in the last CSC.
Joining now. Yeah. He's joining now. Yeah.
She is joining.
Okay.
I just said it.
Good to see familiar faces. It will be very elementary for you. But yeah.
Yes.
Right. So you have a beautiful campus. I picked up some pictures on my past slide, and
Yes, sir.
this is
Really beautiful.
This is in Newtown near the Rabindra Tirtha, or it was Agita?
No. It's near Barashat, the campus is.
Oh, this is near Barasat. This is not
Barasat.
Okay.
No, not in Newton.
Okay. I never saw Barasat like this. I have been there so many times. Oh, this looks beautiful. Yeah.
The picture is quite different inside the campus and outside the campus.
Okay.
Tamal, shall we wait for 5 minutes more?
Yeah, let us wait.
Okay.
Tamal, how are you?
Fine. How things are going on at your end?
It's quite nice. I mean, making video lectures, uploading them in the college websites.
That's good.
It's a different experience altogether.
So the lockdown gave us some new ideas, new way to deal with things.
Yes.
ডিস্টার্ব করছিল আবার
In our place now, very big storm is going on. Not super cyclone, but storm.
Another?
Yeah.
Oh, okay. So, but we are just recovering from one and the another starts. Yeah. So this is the season. Basically, this is the season and one after the other. But in my 20 plus years in Calcutta, I never experienced something which you had.
Yes,
10 days
that's
back.
true. Yes.
So it was really very, very bad. Yeah. But somehow, very quickly, within a week, things became normal. It seemed like people are back to work and things are working. So, yeah, which is a good part. Now we know how to prepare ourselves.
Exactly.
So we go through little bit, bad times and then prepare for that for the next time. So,
Yeah, that's true.
it's the sound of the wind outside.
Yes,
The sound of the wind.
Yeah, actually, it is going on in Delhi region, not in Kolkata. That's what I'm telling. Just it is not so super cyclone, but a very big storm is going on here in Delhi region.
Oh, you're in Delhi?
Yes,
See, you
yes.
can also.
Oh, okay. Oh. So you didn't experience the cyclone, super cyclone?
I didn't experience it because that time I was not in Calcutta.
You were in Calcutta that time?
No.
So you can travel now. Flights are operating, so you can
Yes,
travel at least.
yeah.
Yeah. So lockdown is one thing. To get back to normal, also that needs even more preparation.
It is termed as unlockdown.
Yeah. People call it how to deconfine. So this is what people talk here. So, and that also needs much more planning because lockdown was all of a sudden. We didn't have a choice, and now we have a choice how to open, and that becomes more difficult.
Yes, actually, unlock this mechanism will be conducted in a staggered manner,
Yeah.
step by step. Actually,
Yeah. Right. That's true. That's true. How to be staggering, how to get people back to work and in a safe way. And at CERN, we started in a slow way. Only by middle September, we plan to go back in full swing. Not do that. So only the emergency people who are there during the lockdown. Now, slowly, those who are really required, they are going back. and those who work from home do analysis or do prepare teaching and they stay home. And most of our meetings are all now in video. Yesterday we missed a conference for Large Hadron Physics Conference, 1300 participants, and that was all through Zoom. Oh, and with plenary sessions, parallel sessions. We have many parallel sessions, including posters also. We had a virtual poster sessions. So
Wow.
we need to find new ways to do things.
That's great.
Yeah, that's good.
Hello.
Yes.
Yeah, Tamal sir, how are you? I'm Yogesh from
Hi.
University of Delhi.
Yeah, I can see you. Yeah.
Yeah,
Hi.
hi.
How are you?
Tamal ji,
Everything okay?
good, 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 good.
Yogesh, I follow you through Facebook.
Okay. After a long time, sir, I'm watching you.
Yeah, yeah. Saw your profile, yeah. But Facebook is a good friend. Facebook and Twitter,
Yes, sir.
they are good friends. So I don't miss you because I see your pictures once in a while.
Okay. Thank you, sir.
I see your name at least once in a while. So that, yeah. But it's not the same. It's not the same sitting together and having a cup of coffee.
Yes.
And sir, I also missed you in my international conference.
Yes, yes, I know. Yeah.
Yeah. Anyways, we will arrange another one.
Yeah.
I'm expecting you to come.
I think this lockdown situation should go away very quickly.
Yes,
And
yes.
go back to normal quickly. Yeah.
And how is the situation there, sir?
Situation here is getting better very quickly. Getting very slow, not very slowly, but the curve is going down. The peak
But
already
in Delhi, yeah. But in Delhi, it is very bad.
Yeah. India.
People are not listening even.
Yeah, that's the problem. That's the problem.
Yes.
Here, during the lockdown period, people are really disciplined. Like,
Yes.
we had lockdown finished in about 2 weeks back. Yeah, just 2 weeks from, it will be 2 weeks to Tuesday. And you see people outside without masks playing around, but not many.
Yeah.
And here
Yes,
the population density is also low. The spread probability also goes down with that.
Right.
The modeling becomes, when the model it, when you see a peak and then the decrease of the whole thing, so that becomes easier here. It follows some physics principle. In India, it will be difficult to make a prediction. And I heard a prediction: the peak will be sometime in July, end of July. So that's. But in India, good thing is that the recovery rate is very high.
Yes,
It's about 50% now.
Right.
And in some states even better than that. So it's a good thing that people are getting cured also.
Yes.
Hello, sir. Good evening, sir. How are you? I'm Sudeepa here.
Oh, hi, Sudeepa. Hi.
Seeing you after a long time.
Right. Yeah. Good to see you.
Yes, sir.
So, Tamal sir, shall we start now? Or we wait for 2-3 minutes more?
Maybe 2-3 minutes, then we start.
Okay.
I think let us start.
Hi, Tapals. Professor Tapal, I'm Somarendra from Delhi University. I'm also participating in this conference. And I stay Tamal.
Yes, your voice is breaking. Maybe there is something.
If you want, it's fine.
Yeah.
Acha, the situation maybe because of the rain is coming in the North Delhi.
Okay.
And the Delhi University first. So maybe because of this rain problem with that projects. So nice to see all of you.
Yeah.
Hello.
Yes, here in Delhi region, storm with rain is going on now.
Yeah.
Oh, now we see you, Samendra. And there was the earthquake also a few days
Yes,
back.
last 2 days.
Yes. There was earthquake few days before, and that was mild, not so much.
Yes, yeah. It's 4.3, 4.4 this way, yeah.
Yeah, Professor Raghunath Tau from IIT Indore is trying to join, but
he's trying to join for quite a few minutes, but not being able. Every time I'm admitting him, there is some problem.
Okay.
Is this showing joining, right?
Yes. I think Tamal, now it's time we should start now because we are already 5 minutes late, more than 5 minutes.
Yeah.
Yes, we can start.
Okay, hello everyone. So welcome to this webinar organized by Department of Physics, which is Lockdown, Deconfinement and Quark-Gluon Plasma. And I'm Dr. Moumita from Department of Physics, Adamas University. And now I would like to request our Honorable Dean, Professor Bimal Kumar Sarkar, to address the audience, please. Sir, over to you.
Thank you. This is the School of Science, Department of Physics, Adamas University. The school name now changed to School of Basic and Applied Sciences. So today, the Department of Physics going to start one very good and very relevant and very informative today one seminar online, that is webinar. And our reception person, we are very proud of and honored by his presence, Professor Tapan Kumar Nayak, CERN, NISER, Bhubaneswar, and he is deputy spokesman in CERN, Geneva, Switzerland, and FIAS and FNAS, fellow of National Academy of Science, fellow of Indian Academy of Science, later on will be introduced. And most importantly, Professor Nayak just given his consent to give one lecture today on just on the topic that is Quark-Gluon Plasma. It is very important for high energy material. He will be giving this webinar on this topic. What is just Quark-Gluon Plasma, interacting localized assembly of quarks and gluons at thermal and chemical equilibrium condition. So it is very important, and it is said that it was prevailing just at the starting of the universe like this. So many information can be found from this type of material state, and I'm quite sure and hopeful that Professor Nayak today will explain all these things. And most importantly, this event is really very eventful to the Department of Physics at Adamas University in that sense. The Department of Physics just running some programs from UG, PG to PhD level, and in postgraduate level also we have the subject on high energy physics also there. So we are very fortunate that today Professor Nayak will give us some lecture on this high energy physics as well as astrophysics, and obviously we'll just comprising all of these features already we have in our curriculum. So it obviously will be very helpful for our students in PG level, and also faculty members we can know in an interdisciplinary way also. So I just wish the big success of this event today. And then also we have today with us many distinguished persons from different part of the country even, and associated with students, faculty members, scientists. Everyone is here today. So this is the right platform to share the knowledge, to know about this subject, to know about this aspect, everything. So I wish all the success of this event today. Thank you very much.
Madam, your microphone is off.
Yeah.
I'm sorry. Now I'd like to request our convener, Dr. Tamal Kumar Mukherjee, to please address the audience. But before Sir starts, I want to say I have a request to all of you. Please keep your audio in the mute. If you have any question, please write to us in the chat box. After the webinar session, after the lecture, we shall take up all the questions and try to answer those. And those who are following us in the YouTube live, we have a request. Please put all questions in the live chat box, and we will take up each and every questions after the lecture. So thank you very much. Just put your audio in mute position, please. So Tamal sir, over to you.
Thank you very much. First of all, I would like to welcome Professor Tapan Nayak. Very welcome, sir. We are honored to have you. Most of the people who are working in high energy physics and high energy nuclear physics know Professor Tapan Nayak very well. So, but we are joined by others as well today. So, let me introduce Professor Tapan Nayak very briefly. So, Professor Tapan Nayak is a PhD from Michigan State University in 1990. And he did postdoctoral research from Columbia University in New York. He then joined CERN as a guest scientist and later on joined Valuable Energy Cyclotron Center as scientist position. Presently, he is a scientist at CERN and also associated with NISER Bhubaneswar as visiting professor. He is currently working in the areas of nuclear and high energy physics, phases of nuclear matter, etc. Professor Nayak has published more than 250 research papers in various international journals and numerous working reports for different international research collaborations. He has also associated with various international collaborations like ALI, JARC, WA98, Phoenix, and held leadership positions there. He is a former deputy spokesperson for the ALICE collaboration at that, and his term ended in the last December 2019. He is also the fellow of Indian Academy of Sciences and National Academy of Sciences. And the most important part is that apart from the research activities, the activity engaged in the research program of science propagation among students and has organized many events for school and college students. So let us welcome Dr. Tapan Nayak once again. Sir, please you may start your lecture now. Thank you very much.
Okay. You can hear me properly?
Yeah.
Okay, so my screen you can see also as well. So I keep my video on, unless the bandwidth is very much restricted, I'll turn it off, otherwise I'll keep it on. Okay, let me start. So, Namaskar, Namaskar Kalkata, Namaskar to all of you, wherever you are right now, because during this time with the webinar, you don't know, you can be anywhere and listening to any web talks or any talks like that. So, Namaskar to all of you, and let me start by thanking Tamal to give me chance to talk to all of you today. And the Dean Sir, Madam Head of the Department, and all the faculties of Adamas University, and all of you joining from wherever you are. So today I chose a topic which is close to my research interest for the last 30 years. And I didn't think that I would be using the word lockdown so much. The lockdown, just the word became quite popular within last, I would say 3 months. Basically 3 months before, the word lockdown was not even spoken that much. Lockdown is something called a confinement. You are confined to a space. You are not free to move around. You are wherever you are. You are just staying at one place, and within your own boundaries, you are not free to go out and do anything like that. Deconfinement is where you open up. You are not locked down anymore. You deconfine yourself. And I will give the connection to the QuarkGluon Plasma to the early universe. So the feeling of lockdown is very, very strange feeling. Like in my life for so many years, I never thought that we will be in this situation. Many of us never thought that we would be locked down and not able to get out, do our daily things in daily life. So it's a very strange situation to all of us. Even when I'm talking to you, I don't see who you are, where you are. I just see my empty screen. And I'm becoming completely antisocial that way. When I give a talk to the audience, live audience, I interact, I can see their postures, what they're thinking, or they're listening to me, or they're looking at their YouTube pages when my talk is going on. But here, there is no interaction that way. So it's a very strange feeling. The lockdown feeling is a very strange feeling. We would like to be deconfined as soon as possible. You can imagine that way. So what I'm going to talk about today, in the beginning of the universe, when the universe started, when the Big Bang started 13.7 billion years before, and from a something called a singularity, very high temperature, high density matter, and it suddenly expanded very fast. And many things happened within few microseconds, many things happened. And in the beginning, it was all deconfined. This system was deconfined. And within a microsecond, the universe became confined. The universe went to a lockdown. Not the universe, the fundamental particles went to a lockdown. That lockdown, we want to release them from lockdown, deconfine them to see something called a QuarkGluon Plasma. So my talk today will be very elementary for most of you. And Tamal told me that there will be students, so I prepared in a very elementary way. So please forgive me, most of you, in case it is too elementary, but we can discuss. So let me start with our universe. So our universe, we all know, started with a Big Bang, as I said, 13.7 billion years ago. That is 1320 crore, I think, that many years back. And we want to, the fundamental interest for a long time, for not only scientists, for anybody, to find out how it all started and where we are going, what is it made up of. So these are the things we want to answer, the fundamental questions. In the process, we have huge number of big experiments, large-scale experiment, large-scale technology, everything coming along with that. So I'll come to that at the end. So if you can see my pointer, right? My pointer can be seen. So, okay. So if you start with the Big Bang, there's a dot here. Let's say this is the dot, time t equal to 0, where things started. Then let's move right. This nice picture here, this nice picture is taken by satellite experiments. And this picture, the time t equal to 0, this picture is about 400,000 years after the Big Bang. These are the pictures taken by satellites and also cosmic microwave background pictures. And then if you move out, all the way slowly move out toward the end, up to here, then you see you have where we are today. So today we are at a point 13.7 billion years after the Big Bang. So it's a very, very long time after the Big Bang. So what happened within one few microseconds is something called a quark-gluon plasma. That means immediately after the Big Bang, I've come to that, how all the four forces were united And within a microsecond, the whole thing was made up of quarks mediated by gluons. But within a microsecond, the quarks and gluons combine themselves to form hadrons. And within a minute or something, you have a nucleus formation, and things move very, very fast in the beginning. Then afterwards, now things are moving slowly. It is not, the universe is expanding, but the expansion rate and everything one can calculate, but we are progressing in some way. So my main interest is what happens within this 1 microsecond of the Big Bang, the Quark-Gluon Plasma. So I will explain that and how we tackle it, how we check it, how we look at it in the experiment that I will discuss. So let me see, I see my photo screen. Let me see if I can close it. Yeah, now it is good. So now I can see my whole screen. It's okay. So let's start. So how do we solve the mysteries of the universe? This is very simple. So I'll give two examples. One is I'll tell you two things. One is what are the elementary constituents of matter? What are the matter made up of? Going from matter to the quarks and gluons. Then what are the forces which control the behavior? So let's talk about the forces first. What are the four forces? So we have second. I'm not able to do it. Oh, okay, now it started. Okay, good. So we have what are the fundamental forces of nature? One is something called the gravity. The gravity we all know about. Without gravity, we would be all floating around. So this gravity is between two massive bodies. It's a very weak force and it's a long range force. The next one, which is more into the nuclear side, is called weak force. So it's a weak force is like a beta decay. Beta decay, like a neutron, goes to proton plus electron for neutrino, anti-neutrino. This is a weak force, and this is also within the nucleus, nuclear things it also affects. It doesn't affect us day to day. Gravity affects us day to day. The next thing which affects us is the electromagnetic force. Electromagnetic force is the force between two charges, a positive negative electric field or magnetic field. So this is the most common among all of these electromagnetic. Without the electromagnetic force, I won't be able to talk to you today. The whole thing moves through the electromagnetic waves. The fourth force, which is the strong force. So this is the strong force, which is the most important for today's discussion, is that is the force which holds the atom, inside the nucleus you have protons and neutrons, which holds them together and binds the quarks together. This is the very strong force, it's on the very short range, and it's an attractive force. So I will be discussing the strong force. Now, after the four forces, these four forces in the beginning of the universe, when time t equal to 0, all the four forces are united. They're all one force. It's a grand unification. And slowly the four forces became decoupled, and what we see today are all four in nature. And I'll have one more slide talking about the four forces a little later. Now, the second thing is, after the four forces, you have the structure of the matter. The structure of the matter is like we have matter, consists of atoms. Atom consists of, you have a nucleus at the center, and then the electrons surround the nucleus. They move around in different orbits. But once you go inside the nucleus, you have the neutrons and protons. Neutrons and protons are already at the level of 10 to the minus 13 centimeter, very, very small size. And for a long time, till 1950s, so till the beginning 60s, we thought they are the most fundamental constituents. But then we found they are not the fundamental constituents. Then the fundamental constituents is something called quarks. The quarks are inside the neutrons and protons. These quarks are of the size of 10 to the minus 17 or 10 to the minus 18 centimeter. Very, very small in size. So these quarks are inside the proton or neutron, and the quarks are somehow, which I will come in a few minutes, are locked inside the proton and neutron. They are inside this house here. They can't get out. They're locked. That's what we will be talking about. So how do you probe these things? How do you go from, if you want to see the atom, if you want to see electron, how do you probe these things? For example, if you want to see your blood, how the blood cells look like, you have a microscope. You look at the microscope, you can see the blood cells. You want to see the DNA structure, you want to go to powerful microscope, which is electron microscope. Now, if you want to see the electron and how the nucleus behave, the nuclear properties, you can go to Calcutta VECC cyclotron center. We can do the experiments of cyclotron. We can see nucleus, neutrons, and protons. But if you want to see something like much smaller, like quarks, and you have to build very high energetic accelerators. So these are all governed by basically because of de Broglie. Lambda equal to h by p. So we have the de Broglie constant and the momentum. Lambda is the size. The size, if you want to see smaller size, you need a larger momentum or larger energy. So that's what we will be dealing with today. Now, the important discoveries within the last, let's say, about 100 years. A lot of discoveries happened about 100 years within last century. So you have 1911, you have the Rutherford, who discovered the nucleus from the Rutherford scattering experiment. We all know about, that's more than 100 years back. Then again, Rutherford 1919 discovered proton, the neutron in 1932. Then slowly there are a lot of improvements. You have the muon, pion, kaon, different elementary, different particles. Then antiproton, proton 1919, antiproton 1955. Then you have the neutrino. Then you have the different types of neutrino. In 1964, Murray-Gell-Mann and Zweig, they proposed the quark model. They through mathematics basically, they wrote up this paper saying that you have neutrons and protons who are not elementary, and inside there are quarks. Mathematically, they proved that, and they had a eightfold model based on our Buddhist eightfold way of life. They have an eightfold model of quarks, eightfold model of particles. From there, they thought it has to be elementary particle has to be quarks. In 1968, at the Stanford Linear Accelerator Center in California, so we had experimentally done the experiment to deep inlet scattering electron proton experiment. They discovered the quarks. So this they got Nobel Prize in 1990. Friedman and Kendall, they got Nobel Prize in 1990. 1974, these are the 1968, they discovered something called a light quark. 74, we discovered charm quark, then bottom quark, then top quark. So like that, the discoveries are there from the last about 100 years, or a little more than 100 years. The quarks are like this. They don't have the integral charges. The charges are normally you have electron negative -1, positron +1, but quarks carry fractional charges. Fraction means the quarks can have +2/3, -2/3, +1/3, -1/3 charges like that. So the way the proton neutron inside the quarks are organized, so the proton charge is 1, neutron charge is 0. They organize themselves so that the proton neutron the charges are respected. But inside the proton neutron, the quarks, they have fractional charges, and they have very different many different properties which I am not going to discuss today. There is something called an up quark U. There's something called a down quark, up and down. They are light quarks, only 2.4 MeV their mass. Then 4.8 MeV the deuteron. The charm and strange, they are getting slightly heavier. Strange is about 104 MeV compared to 2.4 here, 104 MeV. With respect to everything, electron is 0.5 mass. Then the charm quark is 1.727 GeV. Charm and strange, there is another family. The third family is something like top and bottom. So bottom is 4.2 GeV compared to this many MeV is 4.2 GeV. It's much more heavier. The top is even more heavier, 171.2 GeV. So the discovery of up and down, these up and down are inside the proton and neutron, not the heavy ones. The up and down were discovered in the beginning, 1968 experiment, then 74 charm quark, then strange quark is a part of the kaon. So kaon was discovered early. So we knew there is something strange going on about it. So that was the strange quark. Indirectly, we knew about it. Then at the bottom quark 77, top quark very recently 95 in Formula, which is in Chicago. The quark has a very the physicists are very good in naming, giving the names to the things. So the quarks, up, down, charm, strange, truth, beauty, or top, bottom. Then they thought that the quarks come in colors, the red, green, and blue. If you mix red and green and blue, you get a neutral color or colorless. So protons don't have color. They consist of 3 quarks, one red, one green, and one blue. Antiproton, which is negative antiproton, they consist of antiquarks. They have anticolors, red, green, and blue. So they are the red, green, and blue that are not really colors. There's some sort of matrix elements which are needed for the mathematical description of the quark structure. So, but then they thought, let's give them the name red, green, and blue. So that works out very well, the traffic light colors. So here is Murray Gell-Mann, who got the Nobel Prize 69 because of the quarks. Moving on. So now let's move on to the lockdown. What is lockdown? Lockdown is quark confinement. That means quarks are confined within the protons and neutrons. If you look at the proton in this picture here and neutron in this picture here, proton consists of 2 up quarks and 1 down quark. The red, green, and blue, they give the colorless. So proton is colorless. Neutron is also colorless. Proton consists of 2 up, 1 down. Neutron consists of 1 up, 2 down. So ultimately what happens, 2 up, 2/3 minus 1/3, they make it charge 1. So this is like charge 0. So this is called something in many different models exist. Like one is the popular model, bag model, MIT bag model, in which this is a boundary in which the 3 quarks, they move around freely. They move freely, but they can't come out. They have a boundary, they don't come out. It's almost impossible to bring them out. I'll have a demo about this. So this is called confinement. So there is we have not seen 3 quarks. We have seen only the quarks inside, indirect in evidence. Then these forces, which are different colors, they are something called a color force. So the color force is very strong. When you pull them apart, the quarks, you can't pull them apart. Color force is so strong, it pulls back again, so they go inside. This is called confinement. Then something called asymptotic freedom. Inside this, when they are very close together, the force is almost negligible. So when they are together next to each other, they are at home, they are within their own home, they can't get out, but they are free to move around in their own home. It's like if together, they don't interact that much. I'm doing my work, my kids are doing their work, my wife is doing her work, so we're all free to work around inside the house, but we can't go out. When you go out, some attraction pulls them back. If I want to go out now, my kids say, no, don't go out because it's not so safe outside. There's a lot of virus moving around. You come back. So we come back again. We get locked down again. So we get confined. We are not deconfined. Although I like to go out and become deconfined, I can't go out. I'm inside lockdown. So this asymptotic freedom, the freedom inside, I am quite free. They say that you can do anything at home. You give your lecture, you watch TV, and you don't have to go out. As long as you don't go out, you don't interact with others, you don't carry the disease inside you. So this is lockdown and confinement. So that's what very familiar to quarks already, and which we didn't know. We are like quarks now. We are inside the complete lockdown. So this phenomenon of confinement and asymptotic freedom was discovered in 1973, 1975 by 2 groups. This group, these 3 gentlemen, David Gross, Pollizer, and Wilczek, because of this discovery, they got Nobel Prize in 2004 for this discovery. So this is a very important, interesting topic for fundamental physics. Moving on. So no one has ever seen a free quark. Let's have a look at the lockdown, how the confinement and asymptotic freedom works. So as I told you, you have proton. Proton doesn't have any color. Let's call it a white, red, green, and blue. So they are bouncing within the boundary. They're moving around within the boundary. So they are there, red, green, and blue. They can't come out. They're bouncing back and forth. They're moving asymptotically freely, happy. Now, because they're colored, it's not real color, but there's a Duplicity Force. Let's say I want to apply huge amount of force. It's like a tug of war. I have a rope, a string, I move the quarks apart. Very strong color field I apply. But the problem is, it's not like the Coulomb force. The Coulomb force, as you go far apart, then the force goes down. When are together, the force is very high. This is not like that. It's different. It's opposite. When you move apart, then the force is growing. The force grows, and force grows so much. Imagine you have a tug of war. So then, at the center, the force grows so much. Then the rope breaks. If the rope breaks, the rope broke here. The rope broke, and the energy is so much that created a quark, a particle and antiparticle, a quark and antiquark. Then what happened? Quark and antiquark, they immediately realize they are alone. They are all left by themselves. They come back to their own bag again. They form a proton again, and there is another quark which combined with another antiquark. They become a major. The protons or the baryons, like protons, neutrons, they are 3 quarks. Here are 3 quarks. The mesons are 2 quarks. Fire. There are 2 quarks. Okay. So this, you see, this is how it is. They can't be far apart. So it's very difficult to put them far apart. Electrons you have seen by itself. Proton, neutron you have seen by itself. Not you, but many of us have seen in the experiments. But quarks only very indirectly. You can't see them directly. So this is what is about lockdown. Now this is governed by something called a quantum chromodynamics. This is the theory which works to put them together. Now, in an electromagnetic interaction, you have Coulomb force, you have positive red, green, and blue, different types of quarks, and the red, anti-red, green, anti-green, blue, anti-blue. So they are mediated by gluons, and the force is like this. So the potential is also, it is a combination because they have charged particles. You have a Coulomb part and a strong part. They are all so they are a combination of that. So the resultant is that you can't put quarks apart. They are always come back to the. Now we want to deconfine them. I talked about confinement, lockdown. We want to deconfine. In the world also, now every country is thinking of deconfine. How do you deconfine? So that's very important procedure, very difficult procedure, how to deconfine. In our case, we want to, in the left side, if you see something called a hadron gas. Hadrons are like protons, pions, kaons, like that. So inside the hadron gas, you have these bubbles. Each bubble consists of 3 or 2 quarks. 3 quarks, proton, neutron, 2 quarks, so pions like that. So in this gas, you have 2, 3 particles, quarks like that, but they are within their boundary. Now, as I told you, you want to deconfine. That means I want to remove the boundary. I want to lock down, de-lock down, deconfine. So when I want to deconfine, I want to remove the boundaries. How do I remove the boundaries? One way is that you compress them. You press them together. You press them so much that the walls break and they become deconfined. Another way, you heat them up. You increase the temperature to very high temperature. So what happens is that you break the boundary. The right side, I show something completely one big bubble, but inside you have red, green, blue, all the particles are moving freely again. This is called a Quark-Gluon Plasma. Plasma in the sense is that there is no boundary, they are some charge in a different charge state, different state of all together quarks and gluons, so that this is called a Quark-Gluon Plasma. I will come to definition of plasma a little later. So, we want to create the experimental list as soon as the quarks were discovered, as soon as the deconfinement theory was discovered in confinement in 1973-75, immediately after that the scientists thought, let's create a big volume of quarks and gluons like the right side in the experiment, so that we can find out what happened in the beginning of the universe. What was the universe like when it was born in the beginning, like so many billions of years back. So that's the idea. We want to create it to understand what happened in the beginning of the universe, what happened in the Quark-Gluon Plasma, whether it was a gas, a solid, liquid, what is the nature of it. So this is what we want to create. So This quark-gluon plasma is a thermally equilibrated state of matter of quarks and gluons. It is deconfined. It is not confined in the hadrons. It is deconfined. This is what we want to see. I want to tell you one more interesting story. This is something called a phases of matter, different phases of matter. We all know about water. Water exists in three forms. You have a solid ice, you have a liquid water, and you have a steam, which is gas stage. So three stages of matter already we know. In our Indian philosophy, many centuries back, people knew about Panchabhuta, five forces. People knew about solid, liquid, gas, Agni or the fire, and the plasma at that time. What is the other one? Air, I think. Vayu, the fifth force, state of matter that time people thought. So these different forms of matter, you have the solid, you add energy or add heat, it becomes liquid, you add energy again, add heat, it becomes gas. You heat up even much more, you can have a plasma. You can have electrical plasma or star, inside the star, some huge electrical field. This plasma, many of you already know about the blood plasma. People talk about coronavirus testing using blood plasma. The blood plasma is not really directly related to the plasma we're talking about, but that plasma is named after something, a Greek word called a jelly type of thing. That's what the blood. They remove the different corpuscles from the blood and then the plasma, they check the plasma. Then the other definition of plasma is a gaseous substance consisting of free charged particles of electrons or ions. So this was identified in a long time back. So these are the different plasma. So today we are talking about quark-gluon plasma. These different forms of matter are different phases of matter. So they go from different one to the other one based on different phase transition. Let's look at the phase transition of water. What's with water? Water has three phases. You have a solid, liquid, and gas. So you start with a solid ice. You heat up the solid ice, then it becomes water. It stays for some time. The ice breaks down, becomes something. You increase the energy, but the temperature is not going up. Then again, at some point, some temperature starts to go up again. It becomes water. You are heating up. Here it becomes water. You are heating up the water. Then it becomes, at some point, you increase the temperature. Increase the energy, but the temperature is not going up. So it becomes steam. It becomes bubbles. So this is the latent heat. It keeps, but after a long time, you can again start to heat up the thing. So this is like a fast order phase transition in water. In water, this temperature and energy, and you can also see this plot, which is very common, and these we read in high school these days, pressure versus temperature in water. You have a solid, you have a liquid, you have a gas, three different forms. Don't get confused with this dotted line. They are only for guidance, but this is the solid state, liquid state, gas phase stage. When they stay together, this is called a triple point. At very high pressure and temperature, we have something called a critical point. This is something like a fast order phase transition. After the critical point, then the liquid at very high pressure and the gas, there is no distinction. They can move around, go from one to the other. So this is the phase transition in water. Similarly, we have, coming back to quarks and gluons, you apply a lot of energy. You apply a lot of energy to a nucleus, and the nucleus is heating up, and then at some stage you have a pions. The pions, you are adding more and more energy, you are boiling the pions. After some time, they don't boil anymore. Temperature is not changing. You are adding more and more energy, temperature is not changing. It becoming constant. But at some point, you add so much energy that it becomes a quartz of energy. The quarks get liberated for a very fraction of a time, very small time. Before they realize, they go back together again. So it becomes a quartz transition in quarks and gluons. You have energy, temperature. This is something like critical temperature beyond which you have a phase transition. So this is a different phase. So like in water, we have three different phases. We have a normal phase with hadron gas here. We have a quark-gluon plasma phase. These two phases are separated by something called different phases of nuclear matter. In this slide, number 14, you have temperature on the y-axis, x-axis is density, or we call the baryon chemical potential, and the temperature in million electron volt. 1 electron volt is something like 11,600 Kelvin. So y-axis is temperature, x-axis is the density. In the beginning, early universe was very high temperature matter, very, very high temperature. So universe came down like this to normal nuclear matter here, normal matter like here. But then this part of the phase space is called hadron gas, so pions. But you apply sufficient temperature and sufficient density, push them together, apply a lot of pressure, apply energy, increase the temperature, that becomes a Quark-Gluon Plasma. So this is the Quark-Gluon Plasma stage, this is the hadron stage. There's a clear distinction between these two, so two different phases. So this is what we want to explore. In the experiment, we try to scan this whole thing like this, try to see where is the critical point. This is first order phase transition. Beyond this is the normal crossover from one phase to other phase. So this is the critical point we want to explore. So first of all, our goal is to look for the Quark-Gluon plasma. The second goal is to find out how they behave, behavior of the Quark-Gluon plasma, behavior of the matter. The third goal is to find out if there is a critical point exists. Then there are very interesting things happening at the very high density matter. It's called the neutron stars. We want to explore that part, and something called a collar superconductor. Okay, let's move on. What happens? These are the different facilities which are coming about. CERN, Large Hadron Collider, Brookhaven National Laboratory, RIG Collider, FAIR facility in Germany. So they are trying to look at this thing. But if you are a nuclear physicist, like we have Michigan State University, GSI, a cyclotron center in Calcutta, we are looking for nuclear phase transition. And if there is another critical point here. So this is called liquid gas phase transition critical point. We want to look at this one. So two very nice, actually very rich physics here. Two different critical points. We want to explore the whole phase space. Coming back very quickly to the Big Bang again, and in a picture which I rotated a little bit, you start with the Big Bang, let's say from the bottom, this time t equal to 0. At time t equal to 0, as I said, all four forces are united. You must have heard about the God particle, the Higgs field, most likely existed around this time, very beginning. So you have the grand unification around this time, so four forces are united. So slowly, the forces got decoupled. You have the gravity first, and then they have electroweak phase transition. But then what happens, up to about a microsecond, around this time, you have the quarks and gluons. Beyond this, you will go beyond this, you have nucleus forms. So within 3 minutes of the nuclear synthesis is happening. Then you have around 380,000 years, you have the first microwave background which formed, and life is long time after, maybe several billion years after. So this is a phase diagram. This is a diagram of the universe, and our interest is to look at this phase, this quark hadron transition, the Quark-Gluon. So how do you go to quark? As I said, the quarks are very small. You need a large energy accelerator to explore the quarks. You have E equal to mc square. You want to see something very small in mass, in size. You need large energy. You accelerate particles. So you collide particles from one side to the other side. You collide, and many particles are coming out. This is how we can form. This is a high density matter. Now, to create the Quark-Gluon plasma, you cannot create with an elementary particle. You cannot have a E plus E minus electron collision or proton collision. Nowadays we see that, but normally you need a large high mass atom like a gold ion or a lead ion. You take that, you take gold ion means you take a atom, strip out the electrons, you have the nucleus, then move the nucleus at the speed of light, and they collide. When they collide, at collision point, you have a very high density, high temperature matter created. From there, you have so much high energy that many particles are coming out. In the experiment, you look at the particles, how they are coming out, and from there, you analyze each and every the characteristics. So we find out what happens at the center. QuarkGluon Plasma. The relativistic heavy-ion collider at Brookhaven or LHC at the CERN are good examples of these accelerators. So here is the picture of relativistic heavy-ion collider at Brookhaven National Laboratory. This collider is, you have starting from very low energy, you have particles are moving at different speed. One is colored as blue, one is colored as yellow. So the particles are moving in opposite directions, the ions, then they collide. They collide at different phases. Two big experiments in which India participated, the STAR experiment and the Phoenix experiment are located here. Now the Phoenix is not there, so we have only the STAR experiment, a big experiment going on here, and that is trying to mostly look for the critical point. The nature of the matter, finding out if the QuarkGluon plasma is formed. Incidentally, the collider, they have discovered the QuarkGluon plasma. Now we know the QuarkGluon plasma exists. So at STAR, we are trying to find out the properties of the QuarkGluon plasma, properties of the phase transition, properties of the critical, and looking for the critical point. So left side is a picture of the STAR experiment taken about 10 years, 15 years back. It started in 2000. We are celebrating 20 years of STAR experiment. And this is a big experiment with more than 500 people. You can see so many people standing here. There is a detector called photon multiplicity detector, which incidentally is a completely Indian detector, and most of it is built in Calcutta, in fact. So including the electronics, including the detector, everything in the factories in Salt Lake and polygons, and we could build the whole detector here. So this detector took data for several years. In 2011, it's decommissioned because it fulfilled its physics responsibility. So here we are looking for onset of the phase transition, when the phase transition starts, and the critical point. Now I want to spend a little more time on the CERN facility, where I am at present. If you are looking at my picture, the background picture is the our experimental area in Alice experiment. It's a nice green area which I put my background. But this topic is quite nice. You see this is a huge globe. This is a big exhibition center, and you can see the tram lines going to the downtown, which is beyond, and you have on this side in the clear day you can see the Alps, the mountain, which is the highest peak mountain range in Europe. And if you can't see it, but if you go a little, okay, here we call CERN, we call Science Without Borders, because what happens is this picture, this ring here, this big ring is 27-kilometer ring, and this part of the ring is on the Swiss side, and you have the airport. You can see the airport strips here, very clearly visible in this photograph. And this is Swiss side, this is French side. About 1/3 in Swiss side and 2/3 in the French side. So the experiments are, this circle here is drawn by hand because there is a tunnel called the Large Hadron Collider Tunnel. It is about 50 to 150 meters underground and 27 kilometers in circumference and going this way. So the particles, you want them to be at the speed of light. They start from a small facility in this area. This is the main campus called Meran, where our offices are here. My office is somewhere here, but I can't see my office. I have not been there for more than 2 months because it is locked down. Anyhow, it starts from here, from a very small gas bottle. It starts from here, hydrogen, or starts from here, slowly particles speed up and then goes to the collider. We have 4 experiments. One is called Atlas, and Alice, CMS, and LHCb. Atlas and CMS, they are proton-proton experiment. They discovered the God particle. They are looking for much more exotic physics, standard model like the QCD, beyond QCD type models. And LHCb is looking for matter-antimatter asymmetry. So when the universe started, the number of particles and antiparticles, you think about particles and antiparticles are exactly the same. If you put a particle and antiparticle together, they annihilate themselves. You have E plus, E minus. They don't. They can't stay at the same place. So they will kill themselves, and a lot of energy will come out. In the beginning, it was like that, but within a very short period, the antimatter disappears. You have only matter. So you have me as a matter, for example. If I have an anti-me, that will kill myself. I won't see myself again. So this is a very interesting study they are doing. What happens to the antimatter? So that experiment. Alice experiment is our experiment, which will spend more time. That is looking for the signatures of the quark-gluon plasma. In fact, all the 4 experiments are now doing heavy ion physics, studying the Big Bang and the quark-gluon plasma at this point. Now, this Large Hadron Collider, it's a large hadron. As I said, hadron is a composite of quarks. So you have either a meson, which is a pion, two quarks or 3 quarks. So Large Hadron Collider means it collides the hadrons, it collides protons or bunch of proton or neutron like in ion, like in lead or gold. It's large scale, 27 kilometer. Hadron means proton or gold or lead. At the speed of light and the collide. It was built between 1998 and 2008 with 10,000 scientists, many engineers. Most of the scientists who built the accelerator are engineers, accelerator engineers, and the engineers are all types of engineering, computing engineering, electronics, mechanical, civil, everything, because 27-kilometer tunnel underground is also not a matter of joke. It also needs a lot of planning, a lot of civil engineers as well, and many from the universities and laboratories all over the world. This is a tunnel, how the picture looks like. I should have picture myself, but anyhow, this is a picture. The tunnel goes like this in 27 kilometers, like this, very large dipole magnets and many things in the tunnel, and inside this big thing, so you have protons, antiprotons, they move in opposite direction, or ion or anti-ion move in opposite direction, or 2 lead ion, not anti-ion, 2 lead ion move in opposite directions and they collide. So it is 50 to 100, 27 kilometer tunnel, 50 to 150 meters below the ground, 2 beams move in opposite directions, about 9,300 magnets. And if you look down, these are the many things. India collaborated with this one, large magnets. India provided large magnets. We had 1,200 big, large dipole magnets, mostly made in India and tested by Indian collaborations. And these all things are sitting on these red color jacks. So all the jacks of 27 kilometer jacks are made in Bangalore. So India contributed tremendously to this LHC effort and the physics. Just let me show you a small moving. The particles start very low energy, go from a booster, they go to a proton synchrotron, another ring, go from this ring to something called a super proton synchrotron. There they gain energy 450 GeV, it's a 7-kilometer tunnel, a 7-kilometer diameter circumference, it's on the surface. Then they go to the Large Hadron Collider. In the collider, they move almost at the speed of light, very close to the speed of light. In this animation, you don't go to the speed of light, but you can get feeling how it is. Then the quarks are inside the proton, neutron, or that, and they collide. Proton is coming from one side, this other experiment, Atlas experiment, and they collide at this point, and the number of particles coming out, you see, in a proton-proton collision, so many particles are coming out from this energy. But if you have a lead-on-lead ion collision, you have, in each collision, you have 20 to 40,000 particles. And in a second, we store like 50,000 collision. See how do I get out? Now I go to the next page. In collaboration, in our experiment, we have 39 countries from 174 institutes, and India is a prominent, close to 2,000 students, undergraduate, graduate, postdocs, graduates, PhD students, postdocs, scientists, professors, engineers, in this pie chart of all different countries. And you see India, we have 125, I think there is more now, 125 scientists, engineers together, and which is 5th largest in the collaboration out of 1900. So from India, we are in Calcutta. We have a big presence, Cyclone Center, Science, Post Institute, University of Calcutta. We have Aligarh, we have Bhubaneswar, NISER and Institute of Physics, Punjab, Guwahati, IIT Indore, Rajasthan University, Jammu University, IIT Bombay, BRC. We have 14 institutes from India funded by DST. Thanks to our funding agency, we have a good participation, very effective participation from India. Our students, postdocs who have done extremely well, and we have many tens of students who have graduated and now well established all around the world. This is how the ALICE experiment looks like now, and this size, if you look, if you like, in this direction is 16 meter by 16 meter, and the depth is 26 meter. And this red thing you see is a magnet. You need a large magnet because the collision beam is moving, if you like, towards my screen and from the opposite side, and they collide at the speed of light, lead on lead. Particles are coming out. The idea is that we want to measure all the particles are coming out, all 20,000 particles or 40,000 out. These particles can be protons, neutrons, electrons, pions, kaons, all types of charmonia, all types of particles, and we want to measure. So surrounding this beam pipe, we have very high resolution silicon detectors, which we don't see now. It is somehow taken out. Then we have the time projection chamber, large. These are like large scale cameras. This inner tracking system, which is there inside, it has 13 billion channels. 13 billion channels which are looking at anything coming out from there. So anything, they're all open. And then we have this thing, which is a big gas detector, and any particles coming out under the magnetic field, if it is a charged particle, they become tracks, they bend, and from the bending radius and from the magnetic field, you can try to find out what is the mass and the charge of these particles. Identify particles from this, and from the energy loss, they lose also energy on their path. Then we have time of flight detectors, some calorimeters to measure various things. So India participated and made something called a photomultiplicity detector. I'll show you a picture. So this is the detector in a sketch. You have particles which are coming out. We have collision which happens here. We have many different particles. India made something called PMD, which is here, photomultiplicity detector. This is mostly built in Calcutta, in fact, and 2009, and it took data till 2018. Till last beam time 2018, it took data. So this is the size, this is the weight, and various different types of detectors. And another detector in which Calcutta plays major role is called the muon arm on this side. And the second session here is fully built by Saha Institute and Aligarh Muslim University combination. This one. So India played a big role in making some kind of detector to measure photons. This is one picture before the detector was installed inside. This is called a muon tracking system. This is Saha Institute photograph taken in Saha Institute. This first picture was in CERN. This is in Saha Institute, and you can see many people, including Professor Vikas Sinha here. There is a chip we made with Saha Institute called a Manas chip, which is used. We participated in something in electronics called a common readout unit. This is very essential to reduce the data volume, and so that we can keep the data. Then we made there is a new proposal. We made a proposal in 2008. Last but not the least, we have computing in a big way into large scale computing. I have to speed up a little bit, it seems to me now. So in one collision, if you have a one lead on lead collision, you see these are the tracks, the real picture. We see so many tracks are coming up, different color means different momentum of particles which are coming out. So it's about 10,000 particles, and this 3D picture, and you get a snapshot of that. The right side picture, it's like the drawings we make in our homes in India. You have beautiful pictures because of the tracks make, because of the magnetic field. With the magnetic field and the charged particle, they make a beautiful, what I forgot, but they make a beautiful picture in fact. Now, this collision, happens on the left side. It's lead, another lead. When they move at the speed of light, they are like pancakes. They collide, Then they go through various phases. Quark-Gluon Plasma, and Quark-Gluon Plasma cannot stay for a long time. They become again locked down to hadrons, and then we can see a snapshot of like that in our measurement, in the experiment. We can do that. So these are the different stages in the experiment. Whatever we measure, we want to kaons, protons, electrons, everything. We want to put it back and try to, how is this Quark-Gluon Plasma? That's the question, and that's what we try to answer. And we know the lockdown, how the lockdown is, that we know. Hadrons we see, we do experiments every day, but we don't do with Quark-Gluon Plasma. So this is what from the measurements we can do, very specific measurements. In these experiments, you know that lead is a very extended object. It's not a pointed object, extended object. It has a 7 point some Fermi, which is radius. That parameter, they can have a head-on collision, a central collision, or a peripheral collision. They just can touch a little bit, a peripheral collision. So we take data from central to head-on collision to peripheral collision, try to analyze and see the difference, and try to see there is a Quark-Gluon Plasma inside or not. I'll show you 3 measurements to show that we have Quark Plasma. Measurement, very simple measurement too. We measure how many particles are coming out within a small ball. Our measurement back to back in a transverse way. So you have 2000 particles here. If I integrate the whole thing, I see that we have about 21 particles in a head-on collision and about 230 particles in a peripheral collision. 1000 particles in one collision is very, very large number. And we are storing many tens of thousand particles. So in each second, we create 3.3 terabyte. And my laptop is only half terabyte. So my 6 laptops get filled up in 1 second. So that data volume we reduce and then we store it. So very large number of produced particles. There is a simple formalism which was by Bjorken, and this is the formalism. You have a extended Quark-Gluon Plasma, the extended hot zone produced. You have a radius of R. What we do is plotted here as a function of energy in collision energy. We have created an energy density. I can tell you, because I don't have time to discuss detail, this energy density produced is about 10 to 20 times more than normal nuclear matter energy density. According to theoretical calculations, if you are more than 5 to 10, you should have a Quark-Gluon Plasma already. So from this indirect measurement, we can try to find out, because you have large energy density, so we have produced the Quark-Gluon Plasma at a reduced heavy-ion collider at Brookhaven National Lab in New York, Large Hadron Collider at CERN. And then we make many plots like this. Many stop in can find out. We can measure a spectrum like this. In the momentum spectrum, we can try to find out the temperature of the system. So about 100,000 times or 200,000 times core of the solar sun. So that's very high temperature. So as I said, 1 electron volt is 11,000. This is 304 million electron volt. Very high temperature. This is the largest ever temperature recorded in the lab. Although indirectly, this temperature doesn't last. This temperature, you can ask what will happen. Why? Nothing happens. This temperature, sorry, minus 20 seconds. This is from photon. One more last example. If you have a Quark-Gluon Plasma, let's say you have a Quark-Gluon Plasma formed like this. There is something we call jets. Jets are like very energetic particles which are coming out back to back, this way and that way. Something coming out that way, we can measure. Something coming through the plasma, it loses its energy. It just rescatters. This interaction is very strong interaction. You have quarks and gluons. rescatters, loses its energy. That loss we want to see. In this plot, if there is no loss, it should be 1. Because it's lost, we see about 0.4. This gives an indication of formation of high density matter. In the experiment, we have about many hundreds of pictures like this to see the energy loss in a very high dense matter through jets, and this is what one of the main measurements to show that we have strongly interacting medium, and we can try to find out the properties of the medium from different types of particles, not only jets, from different types of particles are going through the system, they can give us different energy loss. Okay, so we have proven right now that we have formed the Quark-Gluon Plasma. Now, just to few slides to show that we have not only the physics interest, we have also a lot of technology interest. One is the World Wide Web. So we are all using WWW. Without World Wide Web, we are completely dead by now, because in the lockdown which is going on, everybody relies on our phones. Without the web, we would be completely gone. So 1990, from CERN, they started the protocol, WWW hypertext protocol, because we wanted to collaborate with many people all over the world, and started from 1990. Now, if you look at the map, it's a huge map of anybody. In everybody's pocket, there is a internet phone now. The lower picture shows the Large Hadron Collider, because a large number of data, it shows the grid computing facility. We have to analyze the data, we store in Calcutta here. In India, there are two facilities, one in Bombay for experiment, for the Alice experiment here in Calcutta. We analyze the data. Another important thing is, which everybody uses now, is the touchscreen. Touchscreen was developed by two engineers at CERN, because that time, in 1970s, we wanted to control the accelerator systems through touching this screen. We can put the high voltage, low voltage, like that. So this transparent touchscreen was developed in 1970-73, which everybody using, especially during lockdown in India, especially it became very popular. Anybody who doesn't have a Arogya Shakti, you cannot go from one place to other place. You have to have a phone. If you have a phone, you have a touchscreen. Remember, they developed by high energy physics experimentalists. So these experiments, this technology, and are widespread. It is without people think, what are the people doing right now? What is IT people doing? The electronics people doing? The computing people doing? Now we have the last lockdown or last plague or last cholera. These days, without that, we can't survive. Medical applications, the high coming, you must have in government talking about the hadron therapy in the country. Putting a lot of money right now, even after the lockdown of the accelerators. In Calcutta, we have a medical cyclotron in Varia, near Ruby Hospital. We have medical facilities in many places which use accelerators, hadron therapy. In Apollo facility in Chennai, we have an accelerator which can treat cancers, which can make new isotopes. So these are all because of the development of accelerator physics. Medical imaging, if you have some problem, if I have a cancer, I can see where the cancer cell is because of medical imaging advancement in that. And medical data management analysis is much more important, especially during lockdown. I had some problem last week. I couldn't go to my doctor. My medical data is all with the hospital here in Geneva. So I wrote a mail that, can you check this data? I need a prescription. And within few hours, I have a prescription of a medicine which I can buy. I don't want to go to hospital now because it's not safe to go because of the lockdown. So these are the things which we all are working to advance, and which is CERN is and the Brookhaven and our BCC, Department of Atomic Energy, Department of Atomic Energy, DST, all are playing a major role to advance the new. And we have plan up to 2035-36. After that, from 2040-45, there's a plan to make something called a future circular collider, which would be maybe if it comes along, it will be 100-kilometer tunnel instead of 27 kilometer. 100-kilometer tunnel will be below the Lake Geneva. It is a project which is long-term project, and the project managers, they have worked out a timeline of 75 years. It comes when and all that. It's very, very, very interesting coming up. For young generation, the field is very open and there are a lot of new things happening. So, Big Bang in the early universe. We cannot create a Big Bang now. This was once in a lifetime, or once there, not lifetime, once in a universe lifetime. People talk about many, many universes might be existing, but we know about at least one universe where we have the QuarkGluon Plasma. And when I say WMAP, just one second, when I say WMAP is something the experiments which look at the microwave background. On the right side, we have something called little bang. In the experiment, we are banging only lead on lead, making little bangs called heavy ion collisions. So this happens, we can create anytime we like. We are making billions of little bangs. These billions means really literally billions, and we use something called event by event. Each collision by collision we analyze. We look at something called a fluctuation. Many of our colleagues, students, they are all active in this one. They make a map like this. From this map, we try to go back and see what happens at the little bang. Then we can understand what happened at the big bang. So this is the main goal. And there was one huge event, but we have many small events, little bangs. Little bangs are almost similar in characteristics to the big bang. Now, coming to the last slide. Down this phase diagram again in temperature and density. Lockdown. You see the poor hadrons, they're locked down completely. They can't go out like us. We can't go out for last several weeks, and now people say you have to stay still more. Look at the right, little bit up to the screen, you have the deconfinement, QuarkGluon Plasma. This is a picture from, I think from Digha or Puri Sea Beach. You see so many people, and it's quite, temperature in India is quite warm. Now even in Europe also it is now 25-30 degrees. We like to go to the beach and become like a plasma like that, become one of them, to enjoy life. We can't go there right now unless it is safe to go out. So this lockdown to deconfinement, we are trying to the facilities at CERN, at Bhubaneswar National Laboratory. We are doing something called a beam energy scan, trying to understand the plasma. In future, we have 4 facilities I know about which are coming up in Germany. On the FAIR facility, India is big involved in a big way. Then in Russia, there is a facility coming up only within next year or two called Nika in Dubna. Japan, there is a jet park, there is a facility exists, but they want to look at the high energy aspects. And China is in a big way, they are trying to do everything. They are trying to do, in fact, a FCC, Future Circular Collider, they want to imitate one and make it there. And now they are also looking for big accelerator for the collisions. Okay, so let me stop here. I'm sorry I have taken a little longer period, but I thought it's better to go through it slow and tell you what we are doing. Thank you very much. Stay safe and stay home, and lockdown is over. It's better that we stay indoors so that we protect ourselves and we protect others at the same time. And I'd be happy to answer some of your questions. If I cannot answer, some of my colleagues and students have joined. They will be able to respond to some of the questions as well. Thank you so much. Thank you very much.
Thank you very much, sir. I request Professor Bimal Sarkar to conduct the question and answer session. I am Professor Aparajita Bhattacharya.
Okay, so sir, okay, sir, am I audible? Hello.
Yes,
sir.
Sir, actually, some question comes. Just one by one, I can place in front of you your kind just answer to these questions. First question, one question comes from Professor S. Shamarendra Singh. He's theoretically it is all right, but how to explain experimentally as observable?
Which one?
He is asking.
Your first word.
Yeah, he is asking, sir. Sir.
hear properly, sir?
Yes.
I could
Yes.
understand the question, but not the first one.
Yes. The first one is anticolor confused observable. Theoretically, it is all right, but how to explain experimentally as observable?
Yeah, the color and multicolor both. Sir. So in the experiment, you have color particles which makes let's say proton. If you go to antiproton, then the matrix the, um, for the red, green, or blue, they become anti-red. So experimentally, you have particle, you have antiparticle. You can measure particles, you can measure antiparticles. So measure anti-red or anti-blue or anti-green. So if you measure proton, which is red, green, blue, then you measure antiproton, these colors. So that's, but we are measuring antiprotons, we are measuring antiparticles. Our antiparticles are, we are measuring constantly. It is only in the universe where particles, antiparticles are created. Antiparticles don't exist now, but in the experiments, we have antiprotons and we have antiprotons. We have kaons, we have K plus, we have K minus, and the neutrals, K0. So experimentally we can measure no problem, because they are, as long as they have charge, it's easy to measure, and so these antiparticles have charge, they have to measure. If they don't have charge, like neutral particles, then you have to find experimental methods to measure neutral particles, like photons or neutrons. So the gluons are emitters. So gluons again spin on bosons who are made colors, like they carry that color quantum number. In red quark, for example, there is a color carrier which is the gluons. So glue zero temperature is extremely difficult, but they are low temperature. I don't think they are zero temperature. I may be wrong, but one can check that. But I don't think they're zero temperature. They're just low temperature. The main difference here but other epidemic is that it is conducted, the transmission is through beam, and that's why so it will go down to some extent, to quite a bit large extent, but this is going to be there. So how to protect ourselves, how to protect the world, so we should think in a long-term basis.
Yes, sir. And next, just one query, just come from. Hello. Hello.
Yeah, I can hear now.
Yes. So next, just part coming from Dr. Sulabna Chatterjee. That the query is two part. One is, would you please throw some more light on silicon calorimeters? Number one, and second part, the tungsten, does it, those silicon tungsten calorimeters, are they photosensitive? Light pass through?
Yeah, I understood. I will try, but calorimeter can some measure energy. In our application, in the high energy piece application, we measure large amount of energy, not a small amount of energy. This large amount of energy, in our experiments, when you large and actually I don't picture of, but yeah. So what we did is that we in India started developing this silicon tungsten calorimeter very early on. Even nowhere in the world they had started. Like only in Europe, France, and CERN had started, and that time we started making silicon detectors. We made silicon detectors in Bharat Electronics Limited in Bangalore, silicon detectors, and then tungsten is a very highly dense material. We used to use something called a lead. Lead is like this. lead and with scintillator. We used to measure energy before. Later, incidentally, we went out one of the small farm in a gully, and there is a company. Lead in eye, lead, and you can. And then there is a lead, another scintillator, a neutral particle like a photon or even electron. It is electromagnetic interaction. It goes through lead. When it goes through lead, it creates something called it has many processes. It has a bremsstrahlung. It has a pair production. Particles produce pair for E plus E minus. And this E plus E minus, the pair produce pairs, you have to measure using silicons. So we used lead that time. So then in 2007-8, we thought of, instead of lead, let's use tungsten. Tungsten is much more, and also it is called sour. Neutral particle goes through, it creates bremsstrahlung, which is gives you one electron or one photon, and that goes to again E plus E minus. Then E minus again becomes, then bremsstrahlung gives E minus, and a photon is like that, and a pair product. So in process it becomes something like a sour broad. The sour we have measure. If you have a tungsten, it doesn't let the sour spread that much. It reduces the sour spread. So you can measure, and it is a very high density. So it has energy more which you lose is much more larger. So we started using tungsten. Instead of scintillator, we started using silicon. So that we built in Bharat Electronics Limited and put together everything. The electronics was designed in Bhabha Atomic Research Center in Bombay. We put together and we made the calorimeter, and the calorimeter we did our core tests and got CERN. Now we know that calorimeter is working and we can measure high energy. From 1 GeV particle we can measure with a high accuracy. This detector was approved only last week at CERN. India is participating in a big way, and we have approved that detector. But the question, what your low energy sensitiveness, for that you don't probably, my understanding is you don't need tungsten. Tungsten, a 1 millimeter tungsten itself is like, it's quite high dense. You lose a lot of energy. Nothing left at the end. For low application, the high density tungsten type of material is not needed. So we can use the silicon sensors. The silicon sensors can be used for any purpose where you have. There are a lot of applications that I don't have anything on top of my head, but scanning for sure, we can do very good scanning, and you can find out the. You can localize things within 100 micrometer level very well. But if you want to do instead of some low energy gamma element, also people are doing with silicon detectors. BCC is a pioneer. There are many silicon detectors, but they are using many other type of detectors. Germanium also, IPO germanium detector also. Those are much more effective for low energy experiments. So we can discuss about it. You can send me a mail. We can discuss this part in detail, because it is.
Thank you so much, sir. Thank you so much, sir.
Sure, yeah.
Sir, Professor Aparajita Bhattacharya asking about experimental signature of QGP formation, particularly in the context of strangeness enhancement. Any comment?
Yeah, we have Professor Bhattacharya. We have this beautiful result from Brookhaven and Large Hadron Collider. The strangeness enhancement, strangeness suppression, basically strangeness enhancement. We have this is one of the most important signatures of QuarkGluon Plasma. We have observed strangeness enhancement in a big way, going from proton-proton to lead-lead. You can look up. We have published this last year, 2017. We published a Nature article where we outlined how the strangeness is getting enhanced. The particles where the strange quarks present, how cross-section is increasing and increasing as a function. If you increase the beam energy, the strangeness is going up and up and up. It's increasing. There are different strange particles. You have kaons, you have lambdas, you have cascades, and how the strengthness increases. It's a beautiful, yeah. The strengthness enhancement is one of the major signatures of the quark-gluon plasma, and we have it.
Thank you, sir. Thank you.
Sir, one question from Sudeep Gaurai asking, how does the different equilibrium conditions like thermal or chemical hold in a quark-gluon plasma?
Wow, this is very, very interesting. The equilibrium, the whole system, evolution of the whole system is so fast. You can stop at a particular time and see that what is the temperature, what is the volume, what are the properties, and that one can do. But so your question is thermal equilibrium and chemical equilibrium. So in our experiment, it's very beautifully we demonstrate what happens if I go back to this picture very quickly. This picture here, you have the collision happens, then you have a quark-gluon plasma phase. The quark-gluon plasma phase, we think it's a thermalized systems of quarks and gluons. That means for whatever the small period, small time it exists, maybe Q Fermi, 3, 4, 5 Fermi, it is in some sort of a equilibrated system of quarks and gluons. Then all the theoretical calculations are done based on that. After that, what happens? You have after the QG phase, it becomes some sort of like a mixed phase of quark-gluon plasma and hadron for a short time. Then it becomes a hadron phase. And we, in our concept, we come up with something called a two different type of freeze out. That means when the particles are coming out, at some point they freeze out for the chemical freeze out, where the number of particles are not increasing anymore. The number of particles are not increasing, but the system is in a pressure and temperature, so we can find out the thermodynamic properties of the system. And then the expansion is still happening, just interacting by kinetic interaction. You have the temperature is still going down. So at some point, the number doesn't increase anymore, but they come to thermal equilibrium. So that means the thermal equilibrium, so the number stops, number is not changing, the temperature is not changing anymore. This is one of the major research avenues from our group in Calcutta, especially our students at Calcutta. They are looking for the thermodynamic properties of the matter to find out the thermodynamic properties like the specific heat, the specific heat of the matter, the isothermal compressibility of the matter, the speed of sound. These thermodynamic properties want to find out, because these properties also matter when the phase transition takes place. So at the phase transition time point, these properties also change. So we want to start. So this is a big, good question, and this is a good research activities for our group also.
Sir, then very interesting question. Beyond expectations, she's asking something different, more expectation. What after the quarks we can discover?
Yeah. At this time, if you are going inside the hadron, and we know that quarks are the most fundamental particle, like the way I showed from nucleus to neutron, proton to quarks, and that beyond we don't know, we don't have any evidence, either theoretically or experimentally, they're more fundamental or more that you can break the quarks again. That doesn't exist. That we don't have no evidence. In 1960s, they had the evidence. There are a lot of discoveries which could not be explained just by neutrons and protons. So theoretically they were wrong. So there is no experimental evidence or theoretical calculation which says beyond this. So, but there are new things people are doing. The string theories, there are many other theories. People are talking about QCD model, beyond QCD model, trying to find out extra dimensions. I'm not an expert on that, but this is very, very interesting physics beyond the standard model people are doing. So even experimentally, we are looking for things like this. Even there are last week in the conference there are talks looking for dark matter candidates in our experiment. Some people are talking about gravitational waves type of signature in our experiments, which is extremely difficult. Extremely, I don't know what are the signatures, I don't know what are those. So theoretically, there are a lot of advance in the field. Otherwise, people will not go to FCC, the Future Circular Collider, which at CERN people want to build. That Future Circular Collider is to build, we have discovered particle, like the God particle, which people call. And beyond that, what happens, there are a lot of theoretical predictions, many things we should see. So that's why people want to build new things. So yeah, curiosity, there is something more exists. But as far as substructure of quarks, at least there is nothing that I know of. Maybe somebody attending can comment on that. But as far as that, we don't have any evidence beyond that. But a lot of theoretical calculation. String theory is asking for energy, huge type of energies beyond what we can achieve right now. We look for particles, supersymmetric particles, beyond supersymmetry and all. A lot of advance in theory and experiment also. Experiment is trying to catch up. Theoretical pieces, they come up with ideas. Experimental is trying to catch up and trying to see if it is possible or not possible, if it is proper or not proper. Yes, sir.
Yes. Another question from Harshita Sharma. Can any combination of quarks exist, or there are some rules for their binding?
Yeah, the rules of course are there. They are governed by very interesting rules. They are there. And a very short answer to your question is, there are predictions that we should have composite quark material like we have seen in hadrons, 3 quarks. There should be 4 quarks and there should be pentaquarks, 5 quarks. So recently people have discovered in LHC-B experiments evidences for 4 quarks and 5 quarks structures, systems which exist like that. There are also predictions that we have something called a H divariant, which consists of, which should be 6 quarks, 2 divariant, 2 variant. So it should be 3 plus 3, 6 quarks. So these are all governed by rules, and if it is possible to measure or not, depending on their binding energies, whether how much, what is the lifetime, and whether the energy is sufficient, whether the lifetime is big enough for us to measure. So there are difference for different particles for measurement energy. So easy always. Recent, if you can Google LHC experiments, tetraquark and pentaquark, you will see new discoveries of the pentaquark. And the 6 quark S divariant, some people are working in the, but it is the binding is very small to measure, so we have not been able to measure it so far. So yeah, but the rules exist. The quark model rules are very interesting rules and very strict rules. Okay.
Yes, sir. So then just Dr. Papia Dhara, she is asking, could you please tell me what are the new particles finding through LHC?
There are many. In fact, there are many new particles. The experiment we are working on, the ALICE experiment, we are not in discovery mode of the new particles. So we are the discovery of the new particles are mostly done by proton experiments, ATLAS, CMS, and LHC-B experiments. We are discovering fundamental, like the quarks. As I said, the quarks, up, down, unstrained, top quark. Quarks are already discovered. Top quark is the last quark discovered at Fermilab in 1997, 98, I think. Yeah. The quarks are discovered, but the combination of including quarks, different quarks with different charge particle, different top particle, different, those are being discovered quite often and quite a bit. So in the last weeks, the Large Hadron Collider conference, we had a session on new particles. In fact, so many particles are also discovered at that point. The number of particles are coming out, which are listed here, are only pions, kaons, protons, gamma is photon, E plus E minus, like that. But the new particles can be combinations of many, and there are resonances, resonant particles, which exist very short-lived particles. So it's discovered quite often. You have quarkonia, two charged quarks getting together and that forming different particles, and there are high resonance states also we are discovering. So many new particles are getting discovered. Yes, you are right, and yeah. Send me a mail. We can try to find out the list also from last week's, especially. I'm sure somebody has made a list of new physics and new particles. So I should be able to share with you. Interesting.
Thank you, sir. Thank you, sir, for your.
Yeah, you're welcome.
Yes. So, from Poonam Jain, is FAIR project has any contribution for determining the properties of QGP?
Oh, very interesting. These, let me go back here the last slide. Yeah. So if you look at this slide, you have temperature and baryon density, and you see LHC here and Reek here, and the FAIR is just starting from here to here. I should have pointed out. I think I did in one of my slides. Let me go back there so that I don't want to.
প্রশ্ন করে না মানে
Here, you see the FAIR is at an energy which is almost touching to the critical all the way going up to the neutron stars. So FAIR facilitates a big contribution to we can come up with, and one of the major to my interest is that one of the major things is that we can discover the critical point. I drew it here. This is a point which may not be existing here. It may be here. It may be here. So we want to discuss we discover the critical point. Discover also what happens to the QGP matter at extremely high densities, all the way going close to the neutron stars. So it has a very big contribution of scanning the phase diagram in very high density matter. Very high density matter, you are forming a compressed barrier. The matter which is compressibility is very high. You can compress the matter. Some of our students, my colleagues who are joined here also today in this webinar, working on this FAIR facility, and some are directly looking at compressibility. How our matter we can compress, and what we can learn from this FAIR facility. This facility is going to give us a lot of knowledge about the quark plasma, about the phase diagram, and about the critical point, the phase structure.
Thank you so much, sir. Thank you for enlightening me.
You're welcome, Kumar.
Sir, most probably the audience will very much excited to ask you many things. Another question, and it comes from Yogesh Kumar. One comments he is asking from you. The fact is that since long high energy physics community contributed and helped a lot in searching small particles, so there is any possibility to detect coronavirus-like particles in near future? Your comment is please.
What can I say? Yeah, this is yeah. You should know this answer. You should not ask me. I would like to ask you what is the answer. Coronavirus, the virus size is much larger than quarks or gluons or neutrons or protons and all that. So coronavirus size is maybe 100 micron. I don't know what is the size of the virus. Microns, right? So microns, so millimeters. Micron size. They all consist of. Somebody was asking, and I said all are made up of quarks. In fact, so all made up of quarks. Our instrumentation can help, in fact, in a big way, because you don't know. I think even in our departments, DST, DE, our departments, we have instrumentation which may be useful in some way. We have to think about it. The coronavirus is is just a virus, but it has a lot of chemical properties which is beyond your understanding, my understanding, because even the experts, chemists, and doctors don't understand. Physicists is really it's beyond our physics, but to detect it, if you can use our instrument to some extent. I know that many of my colleagues are using whatever the machinery they have with them to help in detecting the virus, other than making the PPE, forget the ventilator and all that, just to have a better microscope or better electron microscope or in some safe way to measure these things rather than maybe a better, different way. Can we find a screening mechanism in such a way that we don't have to wear the mask? We can screen ourselves properly, very fine mesh in some way, so that we just plug it in our nose, on our nose, and we don't see it. I don't feel like wearing a mask when I go out, but I have to now. So this may be one of the way. But how do we detect the virus? How accelerators will help? I don't know. The radiation therapy helps. So far it is not known. Radiation therapy helps in detecting the cancer and killing the cancer cells, the bad cells, because these are big scale, big size. But the virus is completely invisible. The way it goes to the nose or the mouth and affects the throat, whatever I read in the newspapers is very scary. So, but we have to be scientists. So let's analyze in a science. As I said, maybe we can have a panel discussion ourselves one day, just to discuss on the corona. Thanks, everyone.
Sir, one just a query from Dr. Sabuj Ghosh. Most probably in your slide number 13, this space diagram curve has a non-zero finite width. The curve has a non-zero finite width. Can you comment on this finite width?
Yeah, this is a good point, and people have been this non. It should be 14. Suppose I couldn't hear you. Your voice is not clear.
He's trying to say that it is in the slide number 14. You were in the right slide.
Yeah. And this in the slide number 14. My question.
But your is breaking. It's not clear. But sir, he's probably saying that you are in the slide number 14.
I think he was asking about the width, the width of the. This is a sketch. This is not sketch. That we have a lot of uncertainties in our experimental understanding of this phase diagram going from hydrogen gas to QuarkGluon Plasma. We don't have a sharp line. We don't know exactly the point where the transition from one phase to the other phase takes place. We have huge uncertainty. In fact, we are trying to make new phase diagram these days from our experimental knowledge, which also gives the experimental uncertainty. So these uncertainties come from our knowledge, theoretical, experimental uncertainty basically at this point. So this is just a simple sketch, but the real experimental and theoretical picture, which I didn't put here, that looks a little messy now because a lot of points, lot of also there because of certain temperature measurement and density measurement. So that gives the uncertainty mostly.
Thank you, sir. Thank you very much.
From Priyanka Chatterjee, explain what is gluon actually. I have little confusion between quark and gluon. Sir, what type of matrix used for red, green, blue color?
Yeah, these are mostly, let me stop. Yeah, so these are basically textbook thing to look up. You have the inside the proton. The quarks are actually like subatomic particles. They're like particles. They have their properties and everything. But these gluons are like photons. Photons which are like gamma rays, the form of light, that is the photons. Photons are in a form, photons have their own properties. So gluons are, photon is for the quantum electrodynamics, like electric field, electromagnetic field. Gluon is the equivalent of electricity magnetism. In the electricity magnetism of photon, if you go to chromodynamics, quantum chromodynamics, QCD, you have gluon. That is the equivalence of that. Like photons mediate through different particles in a way, but photon is colorless. There's no color, quantum number doesn't exist. But gluon is color. It's called color because of the they are mediating between two different quarks. So gluons is the mediation because they are the strong interaction mediators. Gluons. So if you have the electromagnetism, that is the photon equivalent of the QCD is the gluon. So you can look gluon and quark in a regular Cordially's book. You'll find all the description and how their mathematics.
And then just as an extension, she asked that how much temperature is needed to make hardened gas to quark-gluon plasma?
How much?
How much temperature is needed to make hardened gas to quark-gluon plasma?
Yeah, how much temperature is needed? So if I have here, for example, in this one, so this temperature, if I have low density, low baryon chemical thing, the temperature is 170 MeV. Beyond 170 MeV, if I am here, then it becomes a gluon plasma. 170 MeV means 1 EV is 11,000 Kelvin, so it's a very high temperature. But if I don't have access to high temperature, I create a high density matter. At a high density matter, like here, my temperature can be low, but I have to make a high density. That also becomes a QuarkGluon plasma. So this is not a unique temperature. The temperature profile is given like this. This is the temperature and the density profile. So that is the profile. So if you are at very low, if you are large hadron collider or Brookhaven, then we create a temperature which is very high temperature and very low matter density, baryon density. But if you have a high baryon density and low temperature also, that is possible. So one of the goals of these experiments, the FAIR facility or low energy experiments at Brookhaven collider, is to find out something called an onset of deconfinement. If you go from low temperature to high temperature, at low temperature, we have a confined, we have a lockdown stage. And to increase the temperature, we want to find out at what temperature exactly you have a deconfined stage. Temperature is some sort of like a transition temperature from one phase to the other phase, the transition temperature. That transition temperature at low density is 170 MeV, and here the transition temperature may be a little low, but your density is very high. So you need a high density, high temperature matter in that sense.
Okay. And Ritija Roy asking, what happens if we keep increasing the energy and pressure on the QGP system?
Wow, that's very nice. So if I can see from here, this is the water. This water pressure versus temperature. So you have a triple point, you have a critical point, and beyond critical point, there are. If you go, there are very exotic type of I forgot what it was called. They're very exhibit type of different type of material with different, not only water, different like helium-4 and all that. They exhibit very, very interesting characteristics beyond that in that stage. This is the beyond critical point. It is not the fast or phase transition, it is the crossover. So you go beyond that, you see very interesting properties in in regular matter, in helium-4 and all that. And what happens to the QGP matter at high temperature? Yes, let's think about it. I have not thought. Maybe one of the guys who is watching, one of my colleagues or friends or some audience can answer this. This is interesting.
It is become ideal gas. I mean, the Quark-Gluon becomes ideal gas particle.
Quark-Gluon stage itself is ideal gas. They follow.
So if you see the graph, then it tends to Stephen Boltzmann limit in the asymptotic way. So if you go on increasing the temperature, so it will become more like ideal gas, not approaching ideal.
But one might just query here. If it is so, is it required for relativistic effect to be included Stephen Boltzmann laws there?
So at high temperature, the particles are already relativistic. So if keep on increasing the temperature, then the relativistic effect will wash away.
Okay.
So it will become thermal particles, thermal spectrum.
Yeah. So Tamal is right. For the QGP stage, we already think that it's close to ideal gas, and Stephen Boltzmann law rule applies. And the question, so that the question beyond doesn't arise, right, Tamal? So it is just all ideal gas at that point.
I don't know what temperature he is talking about, but that's the understanding we have now.
Right. Okay.
And sir, as extension of Ritija Roy's question, she's asking more that once we reach the plasma state, what type of interaction takes place between the particles?
Yeah, there in the plasma state, call it plasma. They are all quarks and gluons, independent quarks and gluons. They're moving freely, but they are bound by the strong interaction. The interactions, the quarks and gluons still interact strongly. Interaction is there. So there's a high density matter. It's a quark-gluon matter. So all these, yeah. So the right. So the strong interaction is taking place still. It is there. The quark-gluon matter. Right. Tamal, it's true. It's there's the because they are free quarks and gluons, so they will be following the strong interaction degrees of the equations. As long as they are not, at very high energy. Once you decrease the energy again.
It's always, there are electromagnetic interaction, but strong interaction is the important.
Strong interaction is involved, right? Yeah. Yes.
Yes.
Hi, can I say something?
Yes.
Yeah, actually what you told that in QGP phase, I think it's more like liquid than ideal gas. Means people are talking about QGP is strongly coupled and KYS is small, it's like liquid, not gas. Am I right, Tamal?
So it is during around the phase transition region, right?
Yeah.
Because that's where you measure it at the temperature. At the
if you increase the temperature, it will go like ideal gas thing, as you told. I think
it approaches to Stephen Boltzmann limit.
Yeah. And again, the last question about that question, if you in QGP phase, then is the mostly is strong interaction than electromagnetic interaction.
Yeah.
Because electromagnetic interaction is too small.
Yes.
And in QGP, the alpha is around 0.3, and in that case, the electric interaction alpha is 1 to 137.
Yes.
So
Yes.
the order of magnitude is just 3.
Yes, exactly.
Yeah. So yeah, you're right. But you have the perfect liquid, which is experimentally now proven also. So we measure something called a flow, and from the measurement which matches with theoretical calculations of eta by s. So very low eta by s. So it's like perfect liquid. So and that very high temperature it goes to Stefan Boltzmann. Yeah. Can I clarify that part?
It is so nice. Just question and session is going on. Nobody just try to stop, but still time is limited. So we will further go for only 2 questions. The last but one is from Antik Bhattacharya, just asking, when we add energy to hardens, then you said after a limiting temperature, the temperature will not increase as we increase its energy, but the
similarity with the water. So you have we have something called a limiting temperature. So you are increasing the energy. Like in water, you are giving more and more heat. You are boiling water on the pot. You are giving more and more heat. But the temperature, if you have a thermometer, the temperature is not going up. The temperature is remaining at steam. Temperature is remaining like 100 degrees Celsius. You have the water bubbles, and the bubbles are getting created in heat rather than increasing the temperature. So I was just showing this one. So if you are increasing the energy, the temperature at some temperature, the order of the pion mass temperature, again limiting temperature is called, the temperature is not going up. So the energy you are giving temperature is not going. That energy is used at that point to create this QuarkGluon Plasma. So this is on the right side. So if you are referring to this picture, this is just a sketch coming from the similarity of the water to this one. So this latent heat which is there, that is the signature of the fast forward phase transition. So we try to see QuarkGluon Plasma, whether the order of transition we have now. So far, the order of transition at this stage is about fast forward transition. Then beyond, at very high temperature, low baryon density, we can be like a crossover. So this transition point between the crossover and the fast forward, that is the critical point, which we are trying to locate, which are not able to locate so far at this point. So in sense, we may these things are this part trying to see the fast transition. In this way, so we increase the energy, the temperature is not going up. So we have also in the experiment, we also plot that, trying to see mean PT versus multiplicity or something like that. We make a plot. We try to see the mean PT or mean transverse momentum is not going up for some time at these beam energies. So we call it a fast forward phase transition. Then when we come to very high energy like Rig top energy or LHC energy, then we try to see that the PT has gone quite a bit high. So that's this points here. So the junction of that is the critical point. So this is what we are trying to look for. That's still not found so far.
Sir, now we come to the last question. It is from Indranida asking that please elaborate the different physics results of PP, p-ion and heavy ion physics. Number 2, PP, p-ion and heavy ion physics.
Okay. So, okay, Indranil knows that, but tell you.
No, Tapan, sorry, interrupt also to the convener. The reason for this is entirely to further elaborate that is between the proton lead and lead, because that is the source of our knowledge of this QuarkGluon Plasma, and so I ask. I know that many people knows in this forum, but I think that it will be good to discuss. That is why I ask. This is the justification from this.
Okay, you have 2 lines, then I will add 5 lines. Indra? Okay, let me add. So, okay, so Indra's question is very valid, and that is the purpose of doing this proton plasma. The main reason why we go to heavy ion rather than going to proton. So, if you look at this case here, these accelerated particles can be in the radically many old experiment, like when the quark was discovered, that is electron-proton scattering experiment, because we are pinpointing something very fine to discover something fine, which is quarks and gluons. And electron, very fine particle, and scattering proton, that discovered the quarks and gluons. In the experiments at Fermilab or the older experiments of LHC, we had proton PP bar, proton bar, or E plus E minus. So these, what happens, very fine particles, very high energy, they are going like this, they are colliding with each other, and you have very high energy concentrated in a very small amount of very small space. That to discover particles is extremely important to do that. But in our case, our purpose is not that. We want to create a big system of high temperature and high density, large system of high temperature and high density. In the before 1980s, before we started this, people used to have ion experiments. People thought, let's make a QuarkGluon Plasma. Plasma is an extended system of quarks and gluons. If you have extended system, you cannot have from a simple proton. You have 2 fine particles colliding, it happens. You know the extended particle, like big systems colliding with each other, big trucks colliding with each other. So we went to heavy ion. That heavy means instead of proton, E plus E minus or E plus E plus, or P plus P minus, we go to lead on lead. When you start with lead has 208 nucleons. Each nucleon means either a proton or a neutron. So 82 protons and rest are neutrons. You are starting with a system which is already very big. If you have a proton, you are starting with 1 proton, 3 quarks, and then they create the energy. If you are starting with heavy ion, you have a large system, 208 and 208 colliding against each other and creating a big system, extended system of quarks and gluons. So in our experiments at Brookhaven and also at CERN, we have 3 different type of things we do. Proton, then we do proton on lead, like this lead. Proton is very fine and a lead is, let's say, like this, and lead on lead. We make a comparison. We compare proton to proton lead to lead to find out what kind of QuarkGluon, whether we have created the QuarkGluon plasma and what is the property of the QuarkGluon plasma. And from the beginning, our belief, our understanding is that if you have a head-on collision of lead on lead, we have the QuarkGluon plasma. Then, when recently, in the very high energy proton-proton collision LHC, we see some signature which look like very similar to what we in QuarkGluon plasma. So, but our main bread and butter to physics is the discovery and the looking for the properties of the QuarkGluon plasma. That is done through lead on lead or gold on gold. We start with a big element and collide. Now, there are 2 different types of collision we do. One, you have a target and something comes and hits that. So you collide only one, you only creates particles. Then, in the old days, we used to do that all the time. Now that is done in fair experiment at GSI. But other experiments facilities are weak. And at LHC, we have a collider. When I have a collision is much more violent. It's a very bad collision. That's what we want to create. We want to create a collision which is very bad, violent collision. The head-on collision is very violent collision. If you have peripheral collision like this, they are not touching each other, just touching with each other, it's not good enough. We want to create a system which is a very large system and with very high energy, very high temperature. So you need heavy ion, heavy ion, heavy ion. So this is what the main difference. At LHC, you have new particles. There are many questions about new particles. New particle creation, you see in proton collision at S experiment or Atlas experiment, or LHCb looking for symmetry between particles and antiparticles. In our experiment, we are looking for heavy ion, so we have heavy particle, heavy and heavy collide. But this heavy and heavy has become very interesting because it doesn't detect new particles, but using the new particle concept, the particles are newly discovered, we know that our heavy ion collision, they are also there. So we try to find out those particles. For example, W and Z bosons, W and Z bosons, these are the weak interaction. Those are covered about 20 years back. Those we didn't think about, that we can detect and use that for studying the properties of the QuarkGluon plasma. And we are doing that. And Indra, who asked the question, his experiment here, not only trying to create new particles, detect new particles, using the new particles to measure the properties of QuarkGluon plasma. So this is very interesting concept, combining elementary collisions PP to proton on lead to lead on, and making a difference in all stages to one the matter created. Thanks, Indra, for this question.
Thank you, Tapan. I actually wanted to ask this question for this discussion explicitly. Thank you.
You're welcome.
So, Professor Nayak, we are so thankful to you for very lucidly explanation, everything given. Finally, just I request, bring my heartfelt request to you. Have you any message to the student that how far the high energy physics will be more exposure to them? Any message from you?
Yeah, I think all topics, all science, I am in favor of science education. All science education is important for all of us, not only students, for all of us. Science is the basic, the bread and butter. So we have to do everything, but science understanding is the basic. And physics plays a major role in all our understanding. In fact, now with the COVID situation, the biological, the doctors, the genetics, they are doing their job. But the high energy physicists, in fact, the training of a nuclear high energy physicist is very, I would say, if it's a good high energy and nuclear physics, is an all around training. If you are a student, you want to know about fundamental physics plus applications in terms of electronics and all types of engineering, computing engineering, the high energy physicists are leading the way, in fact. So everywhere, like the big data. When people started analyzing big data, the big, like the Facebook or Google and all that, they are now talking big data. But we are dealing with big data for a long time. The volume is extremely high. So if you are interested in the high energy physics, the field is very open still. And for example, QuarkGluon Plasma, we started working about 30 to 35 years back. But still, we don't have a complete understanding. Still, we are trying to chart out things. And high energy physicists are the FCC, the Future Circular Collider. They are planning for 75 years from the beginning, start. That means there is substantial amount of physics left for them to do, and it's quite challenging also. So for the students, those who are really interested in physics, I think you have a passion. You have to have a passion and just follow the physics passion and you'll do very well. And coming to the, I think in India especially, in the last 20-25 years, we have many graduated, and at least from my point of view, other people may vary their opinion. The opinion will certainly vary, but depending on our situation. But I think we have about close to 100 students who have graduated, PhD students, and they are placed all over the world in some way or other. But they get a very good exposure in terms of life, I would say, because they move around all over the world, they see different cultures, in addition to fighting with their own group, own people, and own institute, they fight to the rest of the world. It is the science which is you are fighting with anybody from anywhere. So that makes it very challenging. Especially from India, what happens, we become little bit inward bound, like we want to do things ourselves without consulting or without discussing or without challenging, getting by others. We take a life which is simpler to us, and if we get proper thing to do in a daily basic thing, we don't really expose ourselves in a big way. But I would say our students, postdocs, all of us, including me, we have exposed ourselves in a bigger way, so we have a better, little bit different perspective of life, different understanding. So be yourself, try to do well, and I think there is future. That is my personal view. But if you have any question, query, we have many faculties who have joined today in our discussions. You can write to me. You can write to anybody. So I think we should be able to answer the questions, and also there is also not only physics. I think many of our physics students I see more in Germany and Europe. After getting PhD in physics, they go to bank, they go to Wall Street, they go to different companies because of the training is different. So we should keep our ears open wherever what comes. Now COVID gives us some opportunity in some way, in some places. Maybe we have to take advantage of that. That's life. We can't avoid that. So I'm sorry I'm coming in a roundabout way, but I think it's good. Let's continue like that.
So, sir, we are so thankful of your so enthusiastic and motivating talk. Really, it's unforgettable. Everybody will remember. Still, if anybody of the dais have some question, obviously we'll contact you through email, something like this. And I believe that they will be very, very happy to do that one. So now just at the end, I am just taking over to our Aerology department, Dr. Moumita, for further activity. Hello? Hello?
Moumita is probably not there. Maybe Sir Aparajita Bhattacharya can say.
Okay, so then Tamal, just you then continue next session.
No, there is nothing much, but
yes,
I would like to say Professor Aparajita Bhattacharya to say anything.
That you just can start actually.
Thank you, Tamal. Thank you, sir. I'm good.
Yeah, very clear.
Yeah. Thank you for giving me opportunity to give vote of thanks to the people who made this event to happen. So one way. First of all, I would like to thank Professor Nayak. My heartfelt thanks to you for making time for us and giving an inspiring talk with your wonderful experience at this difficult time of lockdown. Then I like to thank our Dean Sir, Professor Bimal Sarkar, for our school, Adamas School, the Dean of Faculty of Science, Adamas University, for his constant scientific encouragement and enthusiasm in all activities of the department and made such events possible. I also like to thank our HOD, Dr. Moumita, for her able leadership and his her sincere effort to make this event possible. I like to sincerely thank Dr. Tamal Mukherjee, Associate Professor of our department. He is the key person of this event and make lots of hard work and continuous effort to make this event happen so wonderful way. Finally, my sincere thanks to all of the faculty members, participants, students who are present and interact in this presentation, making this event very, very successful. Thank you, sir. Thank you for coming. Thank you, everybody.
Thank you very much. Thank you.
Yeah.
Really pleasure. My pleasure to be with you today. And yeah, thank you so much, madam. Thank you, sir.
We're looking forward to get you again in the department.
In person. I would love to come in person and beautiful campus. Like to visit you.
Wonderful department, wonderful campus. You'll love it.
Yeah, it's a nice, and I hope this lockdown gets over very quickly and we go to a deconfined stage and come to you, Adamas, very quick soon. Thank you very much.
Thank you.
Thank you, sir.
Thank you. Have a nice day. Thank you.